Well, welcome everybody. My name is Cristina Itarte. I work as an international sales manager at Kunak Technologies. And today I will be hosting a webinar regarding hybrid networks, the future of environmental monitoring. So let's start with a brief definition of a hybrid air quality monitoring. What is it? A hybrid network is the confluence of sensor-based technology, new measurement paradigms, with traditional regulated reference networks. Near reference monitoring can complement traditional networks by providing real-time data, accurate hyperlocal data, and a higher spatial and temporal resolution in a less expensive way. So for those of you that don't know about the background regarding the current status of air quality instruments, I would like to let you know more about the technologies that are currently in this sector. On one hand, we can find the reference and equivalent instruments, which offer really high data quality. They're regulated and certified. They have been used for monitoring air quality for decades, but they can only monitor one pollutant per instrument, and they also offer really high costs. As you can see, we're talking about pretty big devices, so they offer a really limited spatial resolution. On the other side, we can find the low-cost air quality sensors technology, which offer really poor data quality. I would not recommend to use these kind of sensors in a project where the accuracy of the data is a must. They're not regulated, but they can monitor from 1 to 2 pollutants per instrument. They are very low cost, and as you can see, they're pretty small devices, so they offer a really high spatial resolution. In order to release our technology, the near reference sensor-based technology, we wanted to take the best features of both the reference instruments and low-cost sensor instruments and mix it up. And that's how we released the sensor-based air quality stations, which offer near reference accurate data. There is an approved standard for this type of technology, but the status is ongoing. I will discuss this standard within the next slides. We can monitor several pollutants per instrument. In the case of Kunak, we're able to monitor up to 5 pollutants at the same time. Besides particle matter, we are really cost effective compared to the reference and equivalent instruments. And we offer a really high spatial resolution. As you can see, our stations are not too big. And one of the benefits we provide is that our stations are portable, so you can move them around and place them around in order to get more accurate data from other spots. Okay, so going back to the hybrid air quality networks, in order to set up a hybrid air quality network, it is required to develop a plan, whether deploying a single air sensor or a network of sensors. There are many steps involved in planning and conducting an air monitoring study according to the US EPA. The first step we have to take into consideration is the purpose step, which means determining a purpose for monitoring. It is essential to take the time to establish the question or questions to be answered by the air monitoring study before we develop a plan, which is actually the second step. We need to develop a monitoring plan, including guidance for selecting a sensor that measures the target pollutant with the general features required for the project. Then we go towards the setup step, which means locating a monitoring site, installing the sensors, and designing a sensor network. Therefore, to plan and conduct the collocation to determine how to interpret the sensor data. Afterwards, we can find the collect step. That means that with a measurement plan clearly defined and sensors properly located, it is time to collect the data. Measuring air quality is not as easy as just turning on the device and letting it work and collecting measurements. We need to periodically check that the sensors are functioning properly and that they are collecting quality data. And the final step will be the evaluation step, which means analyzing, interpreting, and communicating and acting towards and on based on our monitoring results. How do we select a suitable sensor for our hybrid network? The US EPA has taken in consideration the following factors I'm going to be talking about. The first one is the detection range and the detection limit. As you may know, pollutants are present in different concentrations in the ambient air, depending on the proximity to the pollutant source. Once you determine the pollutant you need to monitor, you need to ensure that the sensor you choose is sensitive across the entire range of the pollutant. Then we can find the precision and the bias. The precision and the bias determine the overall accuracy of the sensor. Precision is the number of times the sensor reproduces the measurement under identical circumstances. And the bias is the error in the sensor, how much higher or lower than the true measurement does the sensor measure. Then we can find the calibration requirements, which I will be discussing later within the next slides. Then we can find the durability. It needs to be robust for harsh environments, and also durability refers to an air sensor's ability to be moved around, placed around, and to be into portable. So you may take into consideration the weight of the station, that it is light enough in order to be placed around and moved around. Then we can find the enclosure, which means which is the case or structure that contains the sensor and its components and protects these components from water, light, temperature variation, and other different environmental conditions. We might also want to take in consideration regarding the closure, the color of the station. Um, it is better to pick a lighter or a white station than a darker or a black station. Why is this? A darker station will tend to be more overheated due to the direct heat of the sun coming towards it, and this may affect the accuracy of the data. Also, the US EPA recommends to use the AP65 enclosure, which is the more robust one, and I gotta say that Kunak stations comply with this enclosure. Then we can find the usability, which is also the operating life of the sensors, which is such an important factor to have in consideration along with the duration of the project. And finally, we can find the cost, which is the budget you can devote to purchase and maintain the equipment. A sensor's cost may vary greatly depending on the pollutant measured and the degree of accuracy and sensitivity. As you may know, our technology is quite new, so it hasn't been certified yet, but there have been made special efforts to unify data evaluation criteria. Below, we can find different standards, protocols, evaluations, and challenges. Let's start with the first one, which is the European Technical Certification 17660. It's composed by the CEN Technical Committee, which is a committee conformed by a group of experts of the subject, in which our CEO, Javier, and our Chief Scientific Officer, Edurne, take part of. They define the standards for this type of sensor technology. The standard actually defines the performance evaluation of air quality sensor systems. The part one for gaseous pollutants in ambient air has been approved at an European level, and the part two for particle matter, is waiting under approval. Then we can find the US EPA protocol. The US EPA is the Environmental Protection Agency from the United States. It's an agency in charge of environmental protection issues. They do educate about protocols in order to perform a correct use of the sensor-based technologies, such as the case of O3 and PM 2.5. In addition, Kunak has received an honorable mention regarding the wildland fire sensor challenge, and you can find more information about that at our website. Then we can find the INERIS certification. INERIS is the National Institute of Industrial Environment and Risks. They created a certification in order to establish air quality sensor certification for system sensors for measuring outdoor air quality. It is only applicable in France, and this certification only certifies the monitoring of NO2 and PM 2.5. Afterwards, we can find the AAQSPEC, which is the Air Quality Sensor Performance Evaluation Center from the USA. This is an evaluation that was established, evaluation center, sorry, that was established to inform the general public about the actual performance of commercially available low-cost sensors. Our older version of the station has been greatly evaluated by this center, and you can find the reports online at their website. And we are currently waiting for a new report for the last version of our station. Then we can find the AirLab Challenge, which is due by the Air Paris organization. This is a challenge that takes place every 2 years in France and Thailand. These two countries were elected due to the different environmental conditions they present. And this challenge evaluates the performance of the sensors and the accuracy of their data compared to the data provided by the reference equivalent stations. More than 50 sensor-based companies took place last year in the last challenge, and I gotta say that Kunak Air Pro and Kunak Air Light got the first position as the most accurate multi-pollutant sensor for 2 years in a row, 2021 and 2023. And last but not least, we can find the MCER certification, which is the performance standard for indicative ambient particulate monitors. It is a certification given by the UK Environmental Agency, only valid for particle matters, and it indicates that the PM measurements comply with the indicative PM measurements. Kunak Air Pro PM sensor is certified for the PM 2.5 and PM 10 sensors. Regarding the data quality of the air sensor-based technologies, as you can see, the World Meteorological Organization quoted that it is required to perform a correct installation and maintenance to ensure the proper performance of the devices and the quality of the data. Towards that, we find two different methods. First, we can find the quality assurance, which is the appropriate calibration that ensures that the data monitored is robust and accurate. And then we can find the quality control, which means monitoring the long-term performance to ensure it remains calibrated and helps notify the user when it needs to be corrected, removed, or recalibrated. As the scientist Snyder et al. Said in 2013, data of poor or of unknown quality is less useful than no data since it can lead to wrong decisions. Now, I would like to discuss about some of the issues and challenges that we can find on the sensor-based systems. First, we can find the environmental condition effects, nonlinear responses to temperature, humidity, and pressure. This means that when we find different temperature and humidity conditions, sensors may react differently towards one or another. We can also find humidity transients. That means that sensors data may be affected when the humidity changes in ambient conditions. And we can also find hygroscopic effects at high humidity conditions. This happens when there are high conditions of humidity. The particle sensors can be affected and measure more PM than the actual real ones that are at that ambient site. We can also find some cross sensitivities. This means that sometimes sensors can respond to more gases than the one they are supposed to monitor. Regarding the baseline and sensitivity drift, this means that the sensibility of the sensors may degrade over time and it needs to be corrected. And then we can find a specific particle type in each location. PM types can be different hyperlocal environments. It is not the same to monitor particle matter in the streets we're standing right now at than in the next streets because they can really change at hyperlocal levels. How do we at Kunak face those challenges? How do we guarantee the data quality? As at Kunak offer the possibility to either calibrate or correct the sensor drift and even combine both options to get the most reliable data with the highest level of accuracy. We ensure the quality of our data by two different processes on our sensors. First, we can find the manufacturing process. We select the best in-class sensor selection among all OAM sensors. Each sensor is characterized across the full range of temperature and humidity in the laboratory. Once characterized, a specific Kunak convert algorithm is applied to each sensor independently to correct the influence of environmental conditions. Then we calibrate against reference standards. We can secondly find the standard operation procedure on field divided on both options to get the most on the both following options to get the most reliable data. First, we can find the calibration, which means that we adjust the sensor response based on the relation between reference concentration value and the concentration measured by the sensor itself. And then we can find the correction. That means that we adjust the sensor response without using any external reference data. As I said previously, the World Meteorological Organization insists that in order to ensure the proper performance of the devices and the quality of the data, it is necessary to perform a correct installation and maintenance of the stations. As at Kunak wanted to avoid additional costs on the maintenance, and that's why we released the gas hood. The gas hood tool lets you perform a proper calibration using a gas cylinder and a gas hood connected to the station, similar to calibration protocol for reference instruments. This tool that we just released this year ensures the client to avoid additional costs on the maintenance of the device since it does not be sent, it doesn't need to be sent back to the factory for calibration. Therefore, we're avoiding transportation costs and also ensuring the convenience of the customer since it can be done on field within a few minutes. Let's talk a little bit about the benefits of hybrid network monitoring. With a hybrid network monitoring, we can find a more robust network for a region since we integrate the benefits of both reference station and sensor-based devices, which leads to allowing monitoring in remote areas, also more and better data quality. We can find a better understanding of pollution variations. We can also receive a higher density accurate data, which helps final clients to take decisions based on reliability. We can also find a better spatial temporal resolution compared to a network of individual monitoring systems. One of the main benefits of our stations is that they are portable and can be actually relocated in order to collect data in another spot, as I said previously, even in areas that are difficult to access. We can also provide multiple applications. You can use it for different projects and applications. And regarding the pollution sources identification, we provide valuable data that helps identify hyperlocal pollution hotspots and heat maps as well. Regarding this last point, some of the analysis tools that we consider that are important to have in consideration when a hybrid network project comes up are the first one will be heat maps that serve to identify hotspots in an area and variable heat maps to see how they evolve over time. Leakages detection. You can set results that will inform you when there is a pollutant leakage detection. You can also get a better analysis of the data combining the sensors with different meteorological proofs. And thirdly, we can find the PM distribution, which is a particle size analysis tool, including size distribution graphs by mass and by counts. These are some of the analysis tools that our Kunak Cloud offers, among many others. I wanted to present this image. This is a map of the city of Paris. What you see, those yellow dots are the reference stations. This is what we call the traditional approach. In the image, you can see a regulatory station network. I have to point out that these networks operate according to a rigorous set of regulatory protocols, And such a network is expensive to install. And as you can see, there are a lot of spatial gaps where there is no monitoring. And therefore, that means that we're losing data. This is how we complement the reference stations. This is how a hybrid air quality monitoring network will look like. As you can see, it's a more flexible approach. It's still underpinned by reference instrument performance, but taking advantage of compact technologies to make deployment and operation easier and faster. We can provide more information, at hyperlocal levels, and we can complement data for those spatial gaps between reference stations that you could perfectly see in the previous image. I would really like to point out with this image on the idea of how our technology is able to complement the data of the reference instruments and to provide data at hyperlocal levels, filling those spatial gaps that we can find the between the reference stations. We don't want to substitute the reference equivalent instruments, but to complement them. Our proposal for complementing the data accuracy from the equivalent instruments is the Kunak solution, which you can see in the image. I would like to present briefly our solution. The first thing you can see is the Kunak Air Press Station, which is the most accurate and multi-pollutant air quality station. Um, Something important to take into consideration, as I said previously, is that this station is light enough to be portable. Then you can find the smart cartridges, which is the air quality sensor in a smart cartridge format. We offer a proposal of up to 21 parameters divided in gases, particle matter, and meteorological parameters. And then you can find the Kunak Air Cloud, which is the powerful air quality software to manage data insights, therefore to take decisions. Now, I would like to talk about some successful projects we have carried out regarding hybrid networks. The first one was a project that we carried out in France with a regulatory institution. This institution had planned to extend France air quality monitoring network, complementing the data obtained from the reference stations with a hybrid network. We had a large monitoring network deployed around the whole country. Therefore, Kunak stations complemented the information provided by the official air quality network, achieving air quality monitoring at a hyperlocal level. This information helped the region to meet its air quality monitoring objectives with a higher monitoring resolution and to inform and alert the population in case of possible pollution events. This organization was really satisfied with our solution since the stations were portable and were able to be placed in remote areas and to monitor data air quality from places where there had never been air quality monitoring before. The second project we can find is a project we carried out at a mining site in Colombia. The company contacted Kunak with the need to create a mining air pollution monitoring system to validate the air quality at a coal mine in Colombia. The objective was to measure, control, and analyze in real time the environmental impact of mining and the activities carried out in different critical points, and use this information, of course, for decision making in order to improve the air quality in the area. Thanks to the deployed network, it was possible to carry out perimeter monitoring through the mine and also to protect the nearby communities and the mine workers from potential pollution episodes. The advanced analysis of the behavior of the different pollutants provided by the Kunak cloud, as well together with the three salt systems of alerts, helped the company to make early decisions and improve daily activities with alerts of potential pollution episodes. For example, in coal transportation, where lots of particle matter can be released to the air, this tool helped a lot in order to change their daily activities in order to improve them. Then we can find another successful project that we carried out in a wastewater treatment plant in Colombia as well. This client had a problem because they had a river that emitted very strong odors. They already had two reference stations, but they needed more monitoring points. We deployed for this project 10 Kunak air process stations in order to monitor H2S and H3. With this solution, we achieved to control the odor dispersion. We achieved to set alarms whenever there was an H2S leakage, and we identified the main sources of contamination. Another one of the benefits was that with our sensor-based technology, they were able to monitor other gases at PPB levels in a more cost-effective way. And for further questions, you can contact me directly through my email. Thank you very much to all of you for attending. This webinar will be recorded and sent to every person that attended. And in case, as I said, in case you have any further questions, feel free to contact me. Thank you very much and have a nice day.